All right, so we're going to talk about these transfer function factors that I kind of introduced. And what I mean, I just want to kind of continue on with the example that we had previously. So let me go and grab this transfer function. And actually, I'm just going to call it h of s. I don't need to call it v out over I in. I think that's a very strange circuit there with a source called v out. Maybe they just meant v0 or v naught or something, but I don't really like it. So let's just call it h of s. And so this might look like it's in a pretty simple form, but there is a simpler form that we can actually get it into. Of course, we know the poles and the zeros. Let me just bring those over there with us too. I think those are important to have for the sake of what I'm about to do. So we've got the two zeros and the two poles. Oops. Let me just do this. So my poles are in blue, my zeros are in red. And basically, what I can do here is I can rewrite this equation, or this transfer function, by, I can factor, well, first let me just rewrite it like this. I can just write the denominator. I can write the denominator in terms of the poles that we found from the quadratic equation, or the quadratic formula here. And I can write those as s plus 1.55 and s plus 6.45, right? Hopefully everybody agrees with that. And so from here, I can rewrite this, and now I can factor this value out of each of these terms, like the value that I have in each of those terms. I can factor it out so that I am left with 1 plus some function of s, or some term that is in terms of s. So let's do that. So I'm going to write 10 times basically 2 times 1 plus s over 2, right? That's the same thing. If I factor this 2 in, I get the 2. If I factor this 2 in here, I get the s. So I basically just pulled the 2 out. I'm going to do the same thing with the 3. 1 plus s over 3. And then I'm going to do the same thing on the denominator. That's going to be 1.55 times 1 plus s over 1.55, and then 6.45. 1 plus s over 6.45. All right, and so now I can rewrite this. I'm going to take this, but I want you to notice that I can now group all of the constants together. So I can move this, I can move this here. And then I can do the same on the denominator. Move these two together. And now all of this right here is basically one giant constant, which I've already computed, and it comes out to be 6, or very close to 6. So I can rewrite this whole thing as 6 times 1 plus s over 2 times 1 plus s over 3 divided by 1 plus s over 1.55 times 1 plus s over 6.45, okay? And so this is now my transfer function, but it is written in what's called standard form. Okay, so let me copy, I'll paste, and I'll put a box around this because this is important. This right here is standard form for my transfer function. This is, if you want to look at the transfer function standard form, it's going to be equation 14.15 on page 620 of the SATIQ textbook. Okay, so in case you want to see the general form of that, I'm not going to write it out because it's very it's very long because of the way that they generalized it, but you can see there the way that they write this equation out. And basically, this expression is leaving us with you may not notice it yet, but it's leaving us with a bunch of factors that we could multiply together to achieve this same transfer function, which is the purpose of this little box here. It's basically factor 1 times factor 2 times however many factors. In this case, we have 5 factors, or 5 individual terms that are contributing to the behavior of our Bode plots. And so what are those 5 things? Well, let me write it out again here in a different way. I can write this as 6 times 1 plus s over 2 times 1 plus s over 3 times 1 over 1 plus s over 1.55 plus 1 over 1 plus s over 6.45, right? That right there, if I were to multiply this times this times this times this times this, I would get this h of s here, right? I could basically decompose this transfer function into 5 smaller transfer functions. Oh, I wrote a plus sign here. This is supposed to be a multiply sign. I can basically decompose, this transfer function into 5 smaller transfer functions that are all multiplied by one another. Now, why is that useful? This might not seem particularly useful, but I'll tell you why it's useful. The reason is that because we can represent the transfer function as a product of these terms, as a product of these factors, it becomes trivial to sketch the Bode plot for the magnitude, and I'll show you why. Let me move some of this stuff around because kind of run out of terms. I'm kind of run out of space here. I don't want to run out of space. I want to try and get through this all in this video. Let's see what I can do here. Okay, so I'm going to box this. See if it comes out nice. Yeah, okay, good. So these two things are equal to one another. Hope that that's clear. And so why is this useful? Well, it's useful because I could call this 6. I could call this factor 1 of s. Of course, it's not a function of s, but you get the gist. This is going to be factor 2 of s, factor 3 of s, factor 4 of s, and then this one can be factor 5 of s right here. And of course, what I'm doing is I'm just multiplying them all together to get my transfer function h of s. And the reason this is powerful is because if you remember correctly, we have a log rule that tells us that the log of a times b is equal to the log of a plus the log of b, right? That's correct. And so it actually follows that the log of a times b times c and so on is equal to the log of a plus the log of b plus the log of c, and so on. If I keep adding terms to the multiplication here, I keep adding them, and those two things are equivalent, okay? And so that's very useful because when we go to plot the magnitude for our Bode plot, we know that what we do is we take h of s, but we don't just take h of s, we take the log of h of s, log base 10. I'm just going to write log though, and we multiply that by 20, right? That would be how we would plot our Bode plot. And so in this case, because h of s is a product of all these factors, what we really need to do is we just need to take 20 times the log of factor 1 times factor 2 times factor 3 times factor 4 times factor 5, right? And that, I'm running out of room here, big time. Let me just add another page because I didn't even talk about this stuff yet. I'm going to wrap this video up pretty shortly, but let me just copy this over. The key here is that this big complicated transfer function with all this stuff going on can be very easily plotted as a Bode plot because of this log rule that tells me that now I can take 20, basically h of s in dBs can be 20 times the log of f1 plus 20 times the log of f2 plus 20 times the log of f3, and so on. And so all I need to do, is I need to know what the magnitude of each of these things looks like individually, and I can plot those Bode plots, and then I can just sum up their effects, right? So if I were to add, if I had one Bode plot that looked like this, and I were to have another one that looked like, let's just go with another color, and another one that looked like this, and I were to add these together, I would basically get that they add together to be at the same 0 value here, and then this one starts to go up, and then they start to cancel. And so my overall Bode plot would be this green trace here, right? Because at all points, I'm just adding them together. And so this green plot that I just created, oh, I guess I didn't draw it all together, that would be my overall transfer function. So all I have to do is individually sketch these Bode plots, which are not difficult to do because we're basically gonna look at what a constant gain term looks like. We're gonna look at what origin zeros and poles look like, and we're gonna look at simple zeros and poles. I'm gonna leave quadratic zeros and poles out for now because we're trying to get through some of this material and the math gets pretty heavy, and it's just, you know, the same principles apply, but just to keep things simpler, we're just gonna look at these three in this class. But for all we have, it's basically just showing us that we can take advantage of this log rule so that we don't have to plot the magnitude of this crazy thing all at once. We can just break it up into its individual components, sketch each one, and then add their effects to do something just like this. And I'm gonna obviously show what an example of that looks like. In the next video, I'm gonna go ahead and stop this one, and I'll have a quick video where I just talk about these real briefly since I haven't talked about them yet. And then after that, what are we doing? Yeah, then we're gonna get into what each of these terms, magnitude and phase, actually look like, because that's how we're gonna sketch these plots, is we're gonna use this principle right here that we can just take each individual factor and plot its effects and then add them together to get the Bode plot. Okay, so I'm gonna go ahead and end this video right here. I know it's gotten pretty long.